Here we have a right circular cylinder whose radius is increasing at a rate of zero point 0.1 inches per minute, and the height is increasing at a rate of 0.02 inches per minute. And we have to answer these two questions. That is, the first one is we have to determine the rate at which the volume is increasing when radius equal to 4 inches and height equal to 7 inches. And at the same time, we have to determine the rate at which the curved surface area is increasing. So let's try to answer these two questions. So at first, we will write the given information in terms of mathematical symbols. So here I have given the visual representation of what actually is happening. So at some point of time, the height and the radius of a cylinder is given as like this, and it keeps increasing. So as you can see that from visual appearance, as the radius increases as well as the height increases, it's the shape itself is changing a little bit. So we can see that the volume is increasing as well as its curved surface, that is the outer surface area, is also increasing. So it's just a sequence of images which is a good field to understand what actually happens here. So let's utilize this information and convert them to mathematical symbols. Using derivatives, I'm going to write down this rate at which radius is increasing as dr over dt. That is dr by dt. This is given as zero point 0.1 inches per minute. And similarly, I'm going to write down the second information, that is the rate at which height is increasing. I can represent this as dh by dt. This is equal to 0.02 inches per minute. So we have these two information, and using the formula to calculate the volume, that is volume is given as pi times of r squared times h, where r and h represents the radius and height of the right circular cylinder. So let's find out the rate at which the volume is increasing. I'm going to use this volume formula. So therefore volume equal to pi times of r squared h. So first I write the formula. Then I have to differentiate both sides with respect to time. So we can write down dv by dt. If you differentiate volume with respect to time, we get dv by dt. And here we have to be a little bit careful. So we have three quantities, that is pi, this is a constant, r, this is varying, and h, this is also varying. So basically we can understand that pi remains constant. We will not have to do anything. So we just keep it as it is. And then consider these two terms as variables. So we have to utilize the product rule of differentiation. So let's utilize that. In that, I have to differentiate one of the quantities. So let me differentiate the height, keeping the radius as constant, and then I have to differentiate the radius or the other variable. In this case, it is r squared. So I put d by dt of r squared, keeping the height constant. So this is according to the product rule. Now let's continue. So let's expand the right side expression. So we have pi times of this is equal to dh by dt times of radius square plus here we have to utilize chain rule to differentiate r square. So if I differentiate r square using the power rule, I will get 2r, and using chain rule I have to differentiate the radius alone. So when I do that, I get dr over dt, and we already have the h, so I put the h as it is. Now we have all the information with us, so we can plug this information into this to find the dv by dt. So I write down here, this is pi times of, we know dh by dt is 0.02 inches per minute, so I utilize only the numerical without the units. So this is going to be 0.02 times of radius square. So let's go back and see if this information is given. We are also given radius is 4 inches at some point of time. So let's replace that. Let me copy that first. R equal to 4 inches and height equals 7 inches. So at a certain point of time, the radius and height of the cylinder is given as like this. So let's replace this. So I'm going to substitute 4, where it becomes 4 squared plus 2 times of radius. Radius is 4, and dr by dt is zero point 0.1, zero point 0.1 inches. So let me put it as just 0.1 times of height is 7 inches. So let me plug this 7 here. So now we have to plug this values into the calculator and simplify the answer. So when we actually plug this into the calculator, we get approximately 5.92 pi, or if you convert this to decimals, we get it as 18.6 inch cube per minute. Since it is rate of change of volume, we have to put the unit as in terms of cubic units. So that is why I have put this in terms of cubic inches. So the answer for the first part is, that is the rate at which volume is increasing, is 18.6 inch cube per minute, that is cubic inches per minute. Now let's determine the rate at which the curved surface area is increasing, that is we will answer the second question. So let's do that. So for that, I'm going to use the curved surface area formula. Let me copy that. This is shortly written as CSA. Maybe for convention, I put this as C. This is equal to 2 pi RH. So once again, we have to differentiate both sides with respect to time. So when we do that, we get dc over dt, that is the rate of change of curved surface area. This is equal to, once again, I have to use the product rule, keeping the 2 pi as constant. I keep the 2 pi as constant. And when I use the product rule, I have to keep one variable constant. That is, let me keep r as constant, and then differentiate the other variable. That is, this will become dh by dt. Similarly, now I keep the height constant as it is and differentiate only the radius. So when I differentiate the radius with respect to time, I get dr by dt. Now let's plug in the values. We have all the information. So this is 2 pi. We know that we are calculating the curved surface area, the rate at which it is increasing at the same time. So we can utilize this information. R equal to 4 and H equal to 7. So let me put R equal to 4 here and H equal to 7, and dH over dt is 0.02. So we can plug it 0.02 over here. We have a plus times of dr by dt is 0 0.1 inches per minute. So I put 0.1 over here. Now we just have to plug this into the calculator and determine the exact or maybe the approximate value. The exact value is 1.56 pi, and this is approximately equal to 4.9 inch squared per minute. Notice that I have used inch square because we are calculating the rate of area, that is the curved surface area. So area should be in unit square. So that's why I put this as 4.9 square inches or inch square per minute. So this is the rate at which the curved surface area is increasing. At the same time, the volume is also increasing.